Topic is the rank of skew-symmetric random matrix over finite fields. This is joint work with Sang-il, who is my advisor. And I think you will be curious about what is random matrices. So let me introduce some definitions. So in the morning, Professor Jung-Han Kim introduced the notion of random graphs. And it is quite similar. First, a random matrix is a matrix whose entries are mutually independent random variables. So for instance, zero case, we just flip a coin, flip a biased or a fair coin, and decide whether the entry is 0 or 1. And it is independent trials for each entry. So then we may think about skew-symmetric or symmetric random matrices also. So here, skew-symmetric random matrix is a symmetric matrix whose diagonal is 0 because it is skew-symmetric, and upper triangular entries except diagonals. You can imagine, right? Yeah, upper triangular entries are independent random variables. So you flip a coin for the entries for the upper upside of the diagonal, and you just write the symmetric way to have a skew-symmetric matrix. So now we will see the meaning. A skew-symmetric random matrix obtained by using bias or biased coin with tail probably P or hat probably whatever is the adjacency matrix of a random graph G and P. You can imagine, right? So it has some meaning. So let me introduce some problems related to random matrices. The first question one can imagine is, what is the probability that a random matrix is non-singular? So this is quite a famous problem, and over finite fields, Blammer and some other two guys did a very famous paper written in 1996, which is the start of this study. And Cooper answered some questions arose in this paper. And Jeff Kahn, who is pretty famous combinatorist, and Komros also have also proved something. And I think the problem about finite fields is almost done by Kahn and Komros. And over reals, you can imagine the real field and 0-1 matrix. And Tao and Wu did several works. In their famous book, the name is Additive Combinatorics, there's a chapter that explains this problem called literal buffer type problems. And what about skew-symmetric or symmetric case? In this case, some people in early 50s actually counted how many, over finite fields, how many skew-symmetric matrices are non-singular, or symmetric on the symmetric matrix, how many are non-singular. So this is a case for a fair coin, and over reals, Costello, Tao, and Wu also did. So even though this is done by some early people, but it is not that ancient things. So what we showed is an extension. What we showed is an extension of the theorem of KAIST. We'll see. So the classical theorem by KAIST is like this. Over ZQ, the proportion of non-singular 2n by 2n matrices is equal to this value. Why 2n by 2n? Because every, we will see later, but let me explain earlier. Then every, excuse me, I forgot to write skew-symmetric, sorry. Every skew-symmetric matrix has an even rank. So every odd by odd skew-symmetric matrix is singular. So I wrote 2n by 2n here. So notice that let Mn be 2n by 2n skew-symmetric random matrix with symmetric probabilities. So we flip a fair coin. Then as a corollary of this theorem, this classical theorem, we have this convergence, right? And remember this state, and we have main results. So the theorem states this random skew-symmetric matrix is not singular. The probability of that event converges to this value as n grows. So this is a corollary of the classical one, but we found two different proofs of this theorem, and one of our proofs leads us to a further consequence, which is written here. So in the previous theorem, we may allow O1 just constant number of non-symmetric entries. So very small number, if we allow, let's say 100 non-symmetric entries, which means for 100 entries we don't have to flip a fair coin. We just can flip a biased coin. However, the probability is not a serious problem. And let me introduce the proof that gives a further consequence in this theorem. So first, as I said, every skew-symmetric matrix over any field has an even rank. It's not hard to see, so and I think everyone agrees. So let me just skip. And the second lemma is quite important. Let A be an n by n skew-symmetric matrix. And there is a typo because I didn't really care about the, I have to write minus V transpose here. The lemma states, once we have a skew-symmetric matrix, then we have to add a column and add a row, and we want to get a bigger skew-symmetric matrix. Here we add a column V, and here we add minus V transpose, and here we write 0. Then we have another bigger skew-symmetric matrix, right? Then let's call this A, this original one A, and this bigger one A prime. Then the theorem states if V is in the column space of A, then rank is equal. And if not, then rank increases by 2. It is not not very hard to see, because if the original one has, if V is in here, then the rank of this matrix equals to A. So adding this row, we can have 0 or plus 1 on the rank. However, because all the rank are even, we only have plus 0. Similarly, the case 2 can be explained. So, in other words, we may say like this. Co-rank means the full rank minus full possible rank minus the actual rank. Everyone understand? So if n by n, then n minus 3 rank. So we may say like this. So we can see our key theorem in here. Our key theorem is, let AK be the k by k submatrix of Mn, which consists of k by k entries on the top left. I mean, if we have Mn in here, this k by k submatrix on the top left is called AK. And CK be co-rank of AK. Of course, CK is a random variable because AK itself is random because it is submatrix of random matrix, right? So then CK forms a Markov chain which has a stationary distribution. One may ask that what is the Markov chain? Because it is not quite, it is very famous definition in product theory, but it is not very common in combinatorics. So what is Markov chain? Let's see the definition. A sequence of random variables is called a Markov chain if each xk plus 1 remembers only xk, which means this. So no matter how x1, x2 to xk minus 1 was, it just depends on what xk was. So here the term, this one is called the transition probability. In our case, we have the following transition probability because of this one, co-rank increased by 1 or minus 1, and it just depends on the event of this a random vector is in a column space of A or not. So it comes like this. So let me introduce a new definition. Well, this is common, but it is still have to be explained, I think. And let me explain the stationary distribution. And our situation, I'm not gonna explain the notion of stationary distribution very rigorously. I want to describe what our situation is. Our situation is like this. This can be, this can be interpreted as a one-dimensional random walk. Imagine a grasshopper on the real line jumps on the non-negative integers. If it is on k, it jumps to either k plus 1 or k minus 1, as you see in here. And if it is on m, it jumps to m plus 1 or m minus 1. Oh, here is a typo. Sorry. This should be plus and this should be minus. Sorry. So you can imagine the situation. And after a very, very long time, where would the grasshopper be? Of course, it is probability, but I want to say, after a very, very long time, we can just imagine the distribution. The distribution converges as n grows. So the notion of stationary distribution can answer this question. In a good Markov chain, good Markov chain means some kind of three conditions: positive recurrent, aperiodic, and what is called? But forget it. Forget it. We just checked that this Markov chain is good, so believe me. In a good Markov chain, the distribution of xk converges to some distribution called the stationary distribution. And this is independent of x0, the initial distribution. So no matter where the grasshopper was in the first time, we can expect the same distribution after a very, very long time. After a very, very long time. So we have last few steps. And first, we may compute the stationary distribution by this is not hard thing, but if you see Markov chain today, if you've seen just today, but then you can not very comfortable. But transition probability may be interpreted as a matrix if the state is countable. Then let the A denotes a transition probability matrix, and this is a vector which denotes the distribution, probability distribution, and this means X is a stationary distribution. Just AX equals to X. So we can actually solve the equation, and we can get the value. And to get the extended version, I mean, here we may allow constant number of defective entries. We just can, let's see. We just can start from an for a sufficiently large n, larger than that constant. Then it converges to the same limit, so it's quite simple. And I think it is beautiful. And frankly, this computation of the stationary distribution is quite complicated. Even Q binomial theorem is necessary. However, we already know the answer, so we don't have to actually waste our effort. So, for the last conclusion and further remarks. So, as a consequence, a random graph G2n and half is non-singular. Non-singular means the adjacent matrix is non-singular. It's non-singular with a probability about 0.4194 ... Because what I showed this value, if Q is equal to 2, then we have like this: 1/2 times 3/4 7 over 8. Like this. This converges to some value like this. So we may conclude this. And further remarks, and the other proof mainly uses Hughes complement. And one may search what it is, and try as an exercise. It's not very hard. And the general case, using bias coin for every entries, we expect the same result if the coin is pretty good. I mean, if there exists some delta between 0 and 1, such that bounds for every coin flip probability for every entries, then we expect the same result. But we haven't found any proof, because we cannot use the our random walk model, because the transition probability not only depends on the co-rank. So thank you. Enjoy your lunch.